There is a difference between the oldest light in the universe and the oldest light the James Webb Space Telescope was built to find. The first is a faint microwave glow released when the universe was about 380,000 years old. It comes from a time before stars, before galaxies, before any familiar structure had taken shape. Webb does not look directly for that glow. Other observatories have mapped it across the sky. Webb begins later, in the long interval when the first stars were gathering inside clouds of hydrogen and helium, and the galaxies were beginning to shine. That light has been traveling for more than 13 billion years. During the journey, space itself expanded. The waves of light were stretched with it, drawn out of the ultraviolet and visible range and carried into the infrared. By the time they reach our part of the cosmos, they no longer arrive in the colors that left those early stars. They arrive as a weakened, lengthened signal spread across wavelengths the human eye cannot see. This is why Webb observes in infrared. Its segmented golden mirror collects light that has crossed nearly the full history of the universe. Its instruments separate that light into images and spectra, searching for patterns that reveal distance, temperature, chemical elements, and the activity of young stars. A distant galaxy may appear as little more than a small red mark in a field crowded with other objects. Yet, inside that mark is a record of a universe still learning how to build galaxies. One of the most distant galaxies confirmed with Webb is known as Mom Z14. We see it as it existed only about 280 million years after the Big Bang. It is not the first galaxy, and it may not remain the record holder. The frontier moves whenever a fainter source is found, observed again, and measured carefully enough to survive doubt. That is an important part of this journey. Webb is not taking photographs of the beginning itself. It is approaching a horizon made by distance, expansion, faintness, and time. Each observation reaches toward a period when fewer stars had lived, fewer heavy elements had been made, and large galaxies had not yet had billions of years to assemble. The farther back Webb looks, the less familiar the universe becomes. Galaxies appear brighter than some early models expected. Chemical fingerprints appear sooner than simple timelines once suggested. Young systems already contain structure, dust, and active regions of star formation. None of this means that the foundations of cosmology have fallen away. It means the first chapters of galaxy formation were more active, varied, and difficult to predict than the evidence available before Webb allowed astronomers to see. Tonight, the path will follow the light itself. We will begin with the universe before stars, then move into the first ignition of stellar light, the growth of early galaxies, and the instruments that turn faint infrared signals into measured history. Along the way, we will stay close to the difference between what is observed, what is inferred, and what remains beyond the present edge of detection. For now, imagine only a small point of infrared light, arriving at a cold telescope far from Earth. It began its journey before the Milky Way had taken its present form, before the Sun existed, and before the atoms in your body had been assembled inside generations of stars. The signal is faint, but it has crossed almost of cosmic time to be here. The light Webb receives from the earliest galaxies did not begin in a universe already filled with stars. Before those galaxies could shine, there was a long interval when the cosmos held matter, gravity, and the possibility of light, but almost no sources bright enough to illuminate the dark. Astronomers call this period the Cosmic Dark Ages. The name is simple, but the reality was not empty. It was a universe in preparation. After the first atoms formed, space was filled mostly with hydrogen and helium. Tiny traces of other light elements were present, but there was no carbon, no oxygen, no silicon, and no iron. Those heavier elements had not yet been made because stars had not yet existed to create them. The gas was thin, cold, and nearly uniform, yet it was not perfectly smooth. Slight differences in density had been left behind by the early universe. Some regions contained a little more matter than others. Gravity acted on those differences over time. The denser places pulled in more gas, becoming denser still, while the universe continued to expand around them. Dark matter played a central role in this gathering. It does not emit light, and it does not interact with ordinary matter in the same way atoms do. But it contributes gravity. Long before the first stars appeared, dark matter had begun forming small halos, invisible wells into which hydrogen and helium could fall. These halos became the first scaffolding for structure. Inside them, gas collected and compressed. Compression raises temperature, but for a cloud to continue collapsing, it must also release energy. In the modern universe, clouds can cool through many processes involving dust grains and heavy elements. The first clouds had neither. Their cooling options were limited, and that changed the kinds of stars they could form. Molecules of hydrogen provided one of the few available pathways. They could absorb energy from the gas and release it as radiation, allowing parts of a cloud to cool enough for gravity to keep rocking them inward. Within perhaps 1 or 200 million years after the Big Bang, the first stars may have begun to ignite. The exact timing remains uncertain because these stars are too distant and too faint to observe individually with current telescopes. Their existence is inferred from simulations, from the chemistry of later stars, and from the transformation of the early universe. Astronomers often call them population 3 stars. The name can sound as though they came after 2 earlier populations, but the numbering follows the history of discovery rather than the order of birth. Population 1 stars, like the Sun, contain relatively large amounts of heavy elements. Population 2 stars are older and contain fewer. Population 3 refers to the first generation, made almost entirely from hydrogen and helium. They were likely very different from most stars now shining in the Milky Way. Without heavy elements to help their birth clouds fragment into many smaller pieces, the first stars may often have grown to great masses. Some models produce stars dozens or hundreds of times more massive than the Sun. Other work suggests that the population could have included a wider range of masses. No single picture has been settled. What is clear is that the first stars changed everything around them. In their cores, hydrogen fused into helium. In the largest stars, later stages of fusion built heavier nuclei. Their intense ultraviolet radiation poured into nearby gas. Their winds and explosions disturbed the halos in which they had formed. A universe that had been chemically simple began to acquire new ingredients. Carbon began to exist in meaningful quantities. Oxygen, silicon, magnesium, and iron followed through the lives and deaths of stars. When massive stars exploded, they scattered these elements into surrounding space. The next clouds to collapse were no longer composed only of the original light elements. They carried the remains of earlier suns. This is one reason the first stars matter so deeply to the story Webb is trying to read. They may be almost invisible to us as individual objects, but their influence is written into everything that came after. The light of early galaxies was shaped by them. The chemical patterns of later stars carry their imprint. The black holes they left behind may have become seeds for larger black holes at the centers of young galaxies. Their radiation also began changing the state of the universe itself. During the Dark Ages, much of the hydrogen between forming structures was neutral. Its atoms held electrons bound to protons. Ultraviolet light from the first stars could knock those electrons free. Around each new group of stars, a bubble of ionized gas began to grow. At first, these bubbles were isolated. One formed around a young cluster, another around a small galaxy, each surrounded by enormous regions that remained neutral. As more stars appeared and more galaxies assembled, the bubbles expanded. Some met and merged. Over hundreds of millions of years, much of the hydrogen between galaxies became ionized again. This era is known as cosmic reionization. It did not happen at one moment, and it did not proceed at the same rate everywhere. It was a patchwork. Transformation. Dense regions with many young galaxies changed earlier. More isolated regions remained neutral longer. The universe became transparent to some kinds of ultraviolet light only gradually. Webb cannot watch the first star ignite as a clean point in time. Instead, it searches for galaxies living during this transition. Their spectra can reveal how much neutral hydrogen lay between them and us. Their brightness can show how rapidly stars were forming. The shapes of their light can hint at the age of their stars, the presence of dust, and the strength of glowing gas around them. Every early galaxy is therefore more than an object. It is a small lamp inside a changing cosmic atmosphere. Some lamps appear through regions already cleared of neutral hydrogen. Others are viewed through thicker veils. Together, they help astronomers reconstruct how darkness gave way, not suddenly, but region by region. For thousands of years, people learned the night sky by comparing one light with another and noticing which patterns returned. Modern cosmology works across far greater distances, but the act of attention is related. A faint source becomes meaningful when placed among many others. Webb gathers those sources one field at a time. Some will prove closer than they first appear. Some will survive the long process of confirmation. A few may carry light from a period when the first stellar populations were still reshaping the gas around them. Behind every one of those points lies the same transition. Gravity gathered the first clouds. The first clouds made the first stars. And the first stars began to lift the universe out of its long, unlit age. Our first galaxy was not simply a larger version of the Milky Way. It did not begin with broad spiral arms, a settled disk, and a central bulge filled with older stars. Those familiar forms required time. They emerged through repeated cycles of collapse, star formation, collision, and gravitational rearrangement. The earliest galaxies were smaller, more irregular, and more difficult to define. Some may have contained only a few million stars. Others were compact knots of gas-forming stars at a rapid rate. Their edges were not always clear, because the surrounding hydrogen was still flowing inward, and smaller systems were still merging with them. To call one of these objects a galaxy is to describe a structure held together by gravity, containing stars, gas, and dark matter. But near the beginning, those ingredients were still learning how to remain together. A dark matter halo formed first. Ordinary gas fell into its gravitational well. The gas collided with itself, lost energy, and moved inward. Dense regions formed stars, radiation, and stellar explosions, then pushed some of the gas outward again. The first galaxies grew through this repeated movement. Matter arrived. Stars ignited, energy escaped. Gas cooled and returned. Nothing about the process was perfectly balanced. A small galaxy could gain material for millions of years, then lose much of it when a cluster of massive stars ended in supernovae. A neighboring halo could pass close enough to disturb it. Two young systems could merge and become one object with a deeper gravitational hold. Growth in the early universe was not smooth. It happened through accumulation and interruption. This is part of what makes the most distant galaxies difficult to interpret. Webb sees them during brief stages in their development. One may be caught during a burst of star formation. Another may appear just after powerful stellar feedback has cleared gas from its center. A third may be in the middle of a merger, its light divided among several bright knots. A single image does not reveal the whole life of the object. It shows one moment, extended across a distance so great that the moment reaches us billions of years after it occurred. In the deepest Webb fields, early galaxies often appear small. Some occupy only a few pixels. Others are stretched or magnified by the gravity of foreground galaxy clusters. Their apparent shapes can be changed by gravitational lensing, which bends their light before it reaches the telescope. Even when a source is clear, its physical size may be uncertain. The bright region Webb detects could represent the whole galaxy, or only its most active central area. Fainter stars may extend beyond the visible boundary. Diffuse gas may be present but too dim to measure directly. Astronomers therefore combine several kinds of evidence. They examine the shape of the source. They measure its brightness through different filters. They compare the amount of light arriving at shorter and longer infrared wavelengths. They look for a sharp drop caused by neutral hydrogen absorbing light below a certain rest frame wavelength. This drop helps identify galaxies whose light has been strongly redshifted. Redshift does not mean that the galaxy itself is blissfully racing away through space in the ordinary sense. Much of the effect comes from the expansion of space during the light's journey. The longer the light has traveled through an expanding universe, the more its wavelength has been stretched. A galaxy observed at a very high redshift is therefore seen far back in time. But a photometric estimate based on brightness in broad filters is only a first step. Different kinds of objects can imitate one another. A nearer galaxy filled with dust may appear very red. A cool star within the Milky Way may produce a pattern that resembles a distant source. Instrument noise can create a faint feature where no object exists. This is why spectroscopy matters. A spectrum spreads light into wavelengths. Instead of seeing only how bright a galaxy appears through a few filters, astronomers can search for specific features created by atoms and ions. Hydrogen can leave a strong emission line. Oxygen can produce another. The relative positions of these features reveal the redshift with far greater confidence. A galaxy that first appeared as a red point becomes a measured object with a place in cosmic history. Spectroscopy also begins to reveal what is happening inside it. A strong hydrogen emission line can indicate active star formation. Oxygen lines show that earlier stars have already lived and produced heavier elements. The balance between different lines can hint at the temperature and density of the gas. Some spectra suggest radiation from hot young stars. Others may include a contribution from gas falling toward a black hole. The distinction is not always simple, especially when the galaxy is small and distant. One of Webb's most important contributions is not only finding early galaxies, but showing that some of them were already chemically developed. The first stars formed from hydrogen and helium. Heavy elements had to be created inside stars and released through winds or explosions. When oxygen appears in a very early galaxy, it means at least one earlier generation of stars has already completed part of its life cycle. The galaxy may look young to us, yet even within that young system, there is already ancestry. Stars have formed, changed, and died. Their material has entered new clouds. New stars have begun from gas that is no longer chemically simple. This process can happen quickly in cosmic terms. Massive stars live fast. Some survive for only a few million years before returning material to space. Within a few tens of millions of years, a small galaxy can begin to enrich itself. The speed of this change is one reason the early universe has surprised astronomers. Before Webb, models already predicted that galaxies should exist within the first several hundred million years. But the number, brightness, and apparent maturity of some early candidates have required careful re-examination. There are several possible reasons. Star formation may have been more efficient in some young halos than expected. Early stars may have produced more ultraviolet light for each unit of mass. Dust may have affected the observed colors differently than assumed. Some bright sources may contain active black holes. Some distance estimates may change after spectroscopy. And the cosmic volume surveyed by Webb is still small, allowing rare objects to influence early impressions. None of these possibilities requires a failure of the larger cosmological picture. They point instead to the difficulty of modeling matter as it moved from nearly uniform gas into the first luminous structures. Galaxy formation depends on many connected processes. Gravity draws matter inward. Gas cooling allows collapse. Stars return energy to their surroundings. Radiation changes the state of nearby hydrogen. Supernovae redistribute heavy elements. Black holes may heat or expel gas. Mergers reshape the entire system. Changing one part of the model can alter the brightness, size, and growth rate of a young galaxy. The early universe was simple in composition, but not simple in behavior. There is also a matter of scale. A small patch of sky observed by Webb may contain thousands of galaxies at many different distances. Some are nearby enough to show spiral arms and star clusters. Others are so remote that they appear as compact smudges. All of them occupy the same image. Their light arrived together, though it began at different moments across billions of years. A foreground galaxy may be seen as it existed a few billion years ago. Behind it, another may appear from a time when the universe was less than 1 billion years old. Farther still, a faint source may carry light from only a few 100 million years after the beginning. The telescope does not arrange these objects by age. It receives them in one field, layered by distance. Human observers have always used the sky as a record, though the records once concerned seasons, directions, and recurring paths. A star rising at a known place could announce a time of year. Pattern near the horizon could guide a traveler. The sky preserved order because its changes were slow enough to learn. Webb uses a different form of celestial record. It looks not for repetition, but for delay. The farther the light has traveled, the earlier the scene it carries. A deep field becomes a history without written pages, assembled from photons that began their journeys at different times. Yet there is no final image of the first galaxy. There may never be a single object that can be given that title with complete certainty. Galaxy formation occurred across many regions. Different halos crossed the boundary from star cluster to galaxy at different times. The first systems may have been too faint to detect, even with gravitational lensing. Webb may find galaxies descended from those earliest structures, rather than the first structures themselves. Their light can still tell us how quickly the transition occurred. It can reveal when heavy elements appeared. It can show how small galaxies combined. It can help measure how much radiation young stars released into surrounding space. The edge of observation is therefore not a wall. It is a region of fading evidence. Each source becomes harder to confirm. Each spectrum demands more observing time. Each conclusion carries a wider range of uncertainty. Beyond the faintest galaxies Webb can measure, there were earlier galaxies. Before those, smaller gatherings of stars. Before those, individual stars forming inside dark matter halos. And before any of them, gas waiting within the slight unevenness of the young universe. Webb stands far from Earth, collecting the later consequences of those first gatherings. A dim red shape enters its mirror. The instruments divide its light. And a galaxy that existed for only a short time in the early cosmos becomes part of a much longer human attempt to understand how structure first learned to hold. Far from the deep fields themselves, another layer of the story begins with temperature. A telescope looking for the earliest galaxies must be protected not only from stray light, but from its own warmth. Every warm object emits infrared radiation. A human body does it. The walls of a room do it. The telescope would do it too. If Webb were allowed to remain warm, its mirrors, instruments, and supporting structure would glow in the same part of the spectrum it was designed to measure. The faint signal from a galaxy more than 13 billion light-years away could be buried beneath infrared light produced by the observatory itself. So Webb had to become cold. It travels around the Sun near a region known as the second Sun-Earth Lagrange Point, about 1.5 million kilometers from our planet. It does not sit motionless at that point. It follows a broad, looping orbit around it, while Earth and the telescope move together around the Sun. From there, the Sun, Earth, and Moon remain in roughly the same direction. This allows Webb to keep all three behind one enormous sun shield. The shield is made of 5 thin layers, each separated from the next. Sunlight strikes the warm outer layer. Heat escapes from the spaces between the sheets, instead of passing directly through the full structure. On the telescope side, the temperature falls low enough for the mirror and near-infrared instruments to work, without being overwhelmed by their own emission. The arrangement creates 2 different environments on one spacecraft. The sun-facing side holds the solar panel, communications equipment, and many of the systems that keep Webb alive. The opposite side carries the mirror and instruments into permanent shade. One side receives the brightness of the inner solar system. The other looks outward from a manufactured night. The primary mirror spans 6.5 meters. It is assembled from 18 hexagonal segments because a single mirror that wide could not have fit inside the launch vehicle. During the journey away from Earth, the wings of the mirror unfolded. Later, small actuators moved each segment until the separate reflections aligned as one optical surface. The accuracy required is difficult to picture. Light from a distant point reaches every segment at a slightly different place. Unless those segments are positioned with extreme precision, the telescope does not produce one clear image. It produces overlapping copies, each a little displaced. Wavefront sensing allowed engineers to study the pattern of those copies and adjust the mirror step by step. The process turned 18 surfaces into a single working eye. Each segment is made mostly from beryllium, a material chosen in part because it remains stable at very low temperatures. The reflective surface is covered with a thin layer of gold. Gold is not there for decoration. It reflects infrared wavelengths efficiently, allowing more of the arriving signal to continue toward the instruments. A photon from an early galaxy may cross the universe for more than 13 billion years, enter the solar system, strike one of those golden segments, and be redirected through a chain of mirrors toward a detector. The final part of its journey inside Webb lasts only a tiny fraction of a second. Yet, every surface it touches has been shaped, aligned, and cooled, so that as little information as possible is lost. NIRCam, the near-infrared camera, often begins the search. It records images across a range of near-infrared wavelengths. Rather than taking one simple color photograph, it observes through carefully chosen filters. Each filter admits a different region of the infrared spectrum. A very distant galaxy may appear in longer wavelength filters while disappearing from shorter wavelength ones. This is not because the source has turned off. It happens because light below a particular wavelength has been absorbed by hydrogen, while the expansion of space has shifted that boundary into the infrared. Astronomers call such sources dropouts. The filter in which a galaxy vanishes provides a first clue to its redshift. Several filters together trace the overall shape of its light. A source that appears only in Webb's longer near-infrared bands may be a candidate from the early universe. Candidate is the necessary word. An image alone does not secure a place in cosmic history. Dusty galaxies at smaller distances can also look red. Cool stars in the Milky Way can imitate some of the same colors. Faint noise can resemble a source when the data are pushed close to their limit. Researchers test the candidates in many ways. They compare separate exposures. They check whether the source appears in data taken at different times. They examine its shape and position. They estimate how well various models fit the observed brightness in each filter. Only after those tests does a small number of objects move towards spectroscopy. NIRSpec, the near-infrared spectrograph, changes the question from what does this object look like to what wavelengths are actually present in its light. The instrument can observe a single source, a compact region, or many targets across one field. One of its most distinctive tools is a grid containing nearly 250,000 microscopic shutters. Selected shutters open while the others remain closed, allowing light from chosen galaxies to enter while much of the surrounding field is blocked. This lets Webb gather spectra from many faint objects during the same observation. For a deep survey, that ability matters. Telescope time is limited. The early universe is filled with targets that require long exposures. Observing one galaxy after another would leave much of the field unused. With the microshutter array, dozens or sometimes more than 100 carefully positioned sources can be studied together, depending on how they are arranged. Their light is dispersed into narrow bands. A bright line may mark glowing hydrogen. Other lines may come from oxygen, neon, or carbon. A sudden break in the spectrum may show where neutral hydrogen absorbed the shorter wavelengths. When several features line up at the same redshift, a photometric candidate can become a spectroscopically confirmed galaxy. This confirmation is because the source may be almost unimaginably faint. The telescope gathers light for hours, sometimes across multiple visits. Individual exposures are combined, detect corrected. Cosmic rays are identified. Background glow is modeled and removed. The result is not a single untouched picture. It is a measurement built from repeated observations and careful subtraction. That does not make it less real. It is how faint astronomy works. The sky itself contains foreground light. Dust within the solar system scatters sunlight. Our galaxy adds stars and diffuse emission. The telescope and detector contribute their own signatures. To reveal the distant object, researchers must understand each of these layers well enough to separate them. Even then, uncertainty remains. A weak line can be confused with noise. A source may lie too close to a brighter neighbor. A A foreground object may overlap it by chance. Different reduction methods may recover slightly different amounts of light. This is why the oldest known galaxy is not chosen by appearance. It is established through evidence that other teams can inspect, model, and attempt to reproduce. MIRI, the mid-infrared instrument, extends Webb's reach to longer wavelengths. For the earliest galaxies, it may help measure light emitted at shorter wavelengths in the galaxy's own frame, but stretched far into the infrared before reaching us. It can also reveal warm dust and other components that are difficult to separate with near-infrared observations alone. MIRI must be colder than the already shaded telescope. A dedicated cryocooler lowers parts of the instrument to only a few degrees above absolute zero. At those temperatures, machinery built on Earth becomes sensitive to heat that began inside galaxies before Earth existed. The images that reach the public are often shown in color, but Webb does not see color in the human sense. Its detectors count infrared photons. Scientists and image processors assign visible colors to different filters so that structures and wavelength differences can be recognized by the eye. Shorter infrared wavelengths may be mapped toward blues. Longer wavelengths may be assigned warmer tones. The result is a translation. It is not a view a human traveler would see by looking through a window. It is a visual language built from real measurements, designed to preserve relationships that would otherwise remain invisible. The same is true of the deep field images, crowded with thousands of galaxies. Some points are stars in the Milky Way. Some are galaxies whose light traveled for a few billion years. Some come from far earlier periods. Every visible color has been assigned, but every source began with photons that reached the detector. There is something steady in the chain of work. A mirror segment must hold its shape. A shutter must open when commanded. A detector must record a minute change in charge. A clock must mark the exposure. A spacecraft must maintain its orientation while distant light accumulates. And on Earth, a researcher must decide whether the pattern in the data is best explained by a galaxy, a foreground object, or chance. While you rest beneath an ordinary ceiling, Webb continues along its orbit beyond the Moon, keeping its shield toward the Sun and its mirror toward space. It does not feel the age of the light it receives. It does not distinguish a nearby star from an early galaxy with curiosity or surprise. It follows instructions. It turns. It settles. It collects. Meaning enters later when the signal is compared with the laws of physics and with everything already known about the universe. The oldest light Webb can find is therefore not discovered by the mirror alone. It emerges from an entire system. Cold surfaces, infrared detectors, selected filters, open shutters, long exposures, orbital stability, mathematical models, and patient doubt. At the far end of that system is a galaxy so distant that its visible light has been stretched beyond human sight. At the near end is a set of numbers stored in a detector. Between them lies almost the whole age of the cosmos, gathered one photon at a time. Once the spectrum has been gathered, the oldest light begins to reveal when it left its source. The measurement is called redshift. Its name comes from a simple movement across the spectrum. As light is stretched along a wavelength, it shifts toward the red end of visible light, and then beyond it, into the infrared. For the galaxies Webb observes near the edge of its reach, the shift is far greater than any change the human eye could follow. Light that began in the ultraviolet may arrive at Webb in the near-infrared. Light that began at visible wavelengths may be carried into the mid-infrared. The source has not changed color in the ordinary sense. The space crossed by the light has expanded during the journey, lengthening each wave. Astronomers describe the amount of stretching with a number known as Z. A redshift of 1 means the observed wavelength has become twice its original length. At a redshift of 10, it has become 11 times longer. At a redshift above 14, ultraviolet light emitted by a young galaxy can reach Webb at wavelengths more than 15 times its starting length. The number is not a direct reading of age. To turn redshift into cosmic time, researchers use a model of how the universe has expanded. That model includes the present expansion rate, the amount of ordinary matter, the influence of dark matter, and the effect attributed to dark energy during later cosmic history. With those pieces in place, a measured redshift becomes an estimate of when the light was emitted. For Mom Z14, the confirmed redshift places the galaxy about 280 million years after the Big Bang. The photons reaching Webb today began their journey when the universe had lived through only a small fraction of 1% of its present age. That does not mean the galaxy is now sitting 13 billion light-years away, at the same distance from which its light departed. The universe continued expanding while the photons traveled. The galaxy's present distance, within the standard cosmological picture, is much greater than the simple travel time multiplied by the speed of light. This difference can feel strange because daily experience gives distance and travel time a stable relationship. A road does not lengthen while a vehicle crosses it. The space between two rooms does not expand while a person walks through a house. Across cosmic distances, the path itself changes. The light keeps moving locally at the same speed, but the scale of the universe grows around its journey. New space is not being added from an outer boundary. Instead, distances between widely separated regions increase as the geometry of the universe evolves. This is why astronomers use several kinds of distance. Look-back time describes how long the light has traveled. Comoving distance describes the present separation after accounting for expansion. Luminosity distance connects an object's measured brightness with the light it emitted. Angular diameter distance helps interpret how large an object appears on the sky. Each answers a different question. For a listener following the history carried by the light, look-back time may be the most intuitive. Webb receives a signal that has traveled for more than 13 billion years. The galaxy appears not as it is now, but as it was when those photons escaped. Its present condition cannot yet be known. It may have merged with neighboring systems. Its stars may have enriched later generations with heavier elements. Its dark matter halo may have grown into a much larger structure. The object Webb sees may no longer exist as a separate galaxy at all. Astronomy does not observe a single universal present. Every direction contains delay. The moon appears a little more than a second in the past. The sun appears about 8 minutes earlier. The nearest stars are seen years before the current moment. The Andromeda galaxy is viewed roughly 2.5 million years ago. Deep fields extend this ordinary delay across almost the full age of the cosmos. A Webb image therefore contains many versions of the past at once. A nearby galaxy may appear from hundreds of millions of years ago. A more distant one may be seen several billion years earlier. Behind both, a small red source may come from before the universe was 300 million years old. The objects share an image, but not an era. Their light meets only at the telescope. Redshift helps separate those eras, though the measurement is not always straightforward. In the early universe, one of the most useful features is associated with hydrogen. Photons energetic enough to interact strongly with neutral hydrogen are absorbed as they pass through gas between the galaxy and Webb. This creates a break in the observed spectrum. On one side of the break, little light survives. On the other, the galaxy becomes visible again. As the redshift increases, the break moves to longer infrared wavelengths. NIRScam can first identify the pattern across its filters. A source disappears in the shorter bands and appears in the longer ones. NIRSpec can then spread the light more finely and locate the break with greater precision. For some galaxies, emission lines offer additional confirmation. Hot stars energize gas around them. When electrons return to lower energy states, atoms and ions release light at characteristic wavelengths. Hydrogen, carbon, oxygen, and other elements can leave distinct features in a spectrum. Because the original wavelengths are known from laboratory physics, the amount of shift can be calculated. If several features have all moved by the same proportion, they form a consistent redshift pattern. The galaxy's position in time becomes more secure. At the highest redshifts, however, strong lines are not always available. The source may be too faint. Its chemical composition may produce weak features. Neutral gas surrounding the galaxy may absorb part of the signal. The exposure may collect enough light to reveal the broad break, but not enough to isolate every line. Confirmation then depends on the total pattern, the quality of the data, and the removal of alternative explanations. This is why a claimed distance can change. A galaxy selected from images may receive a high photometric redshift. Later spectroscopy may confirm it, move it to a nearer time, or show that it belongs to a different class of object. The correction is not a failure of observation. It is the movement from possibility toward measurement. At the limits of detection, uncertainty is part of the result. A spectrum may indicate a narrow range of redshifts rather than one perfect value. The age assigned to the galaxy also depends slightly on the cosmological parameters used in the calculation. As those parameters are refined, the estimated time can shift. The larger story remains stable. The light began when the universe was young, but scientific language protects the smaller details. Approximately. The data indicate. The spectrum supports. These phrases are not signs of hesitation. They mark the boundary between what the detector recorded and what a model allows researchers to infer. The word oldest also requires care. A galaxy may hold the record for the highest spectroscopically confirmed redshift. Another may be a promising candidate at a greater estimated distance, but lacks sufficient spectral confirmation. A third may contain older stars, even if the galaxy itself is observed at a later cosmic time. There are several ways for an object to be old. The oldest light received from a confirmed galaxy refers to the earliest observed moment. The oldest stars within a galaxy refer to when its stellar population formed. The cosmic microwave background is older still because its light was released before any known galaxy, and the first starlight may have appeared before the earliest galaxies. Webb can currently confirm. Webb approaches that first starlight indirectly. It finds galaxies close enough to the beginning that their stars may belong to early generations. It measures the radiation that escaped from them. It searches for chemical simplicity, unusual brightness, and signs that ionizing photons were changing the surrounding hydrogen. Yet the first individual stars may remain below its sensitivity. A lone primordial star at those distances would usually be too faint. Even a cluster may be difficult to separate from the galaxy forming around it. Gravitational lensing could occasionally magnify a star or small enough to make detection possible. But such alignments are rare and their interpretation is demanding. The telescope may therefore find the effects of the first stars before it finds the stars themselves. Their radiation altered the gas, their explosions created heavy elements, their remnants may have seeded black holes. Their descendants shine inside the galaxies now visible to Webb. The oldest accessible light becomes a trail of consequences. This trail extends through the spectrum of Mom Z14. The galaxy is bright enough to have been noticed and measured, despite the immense distance. That brightness presents its own question. Galaxies so early in cosmic history had little time to gather gas, form stars, and build luminous populations. Finding one bright example does not mean every early galaxy looked like it. A deep survey favors objects that can be detected. The brightest galaxies rise above the background first. Fainter and perhaps more typical systems require longer observations, stronger gravitational magnification, or future telescopes. The frontier is shaped by sensitivity. Imagine a shoreline visible at night from far out at sea. The first lights noticed are not necessarily the first houses built, or the most common structures on land. They are the lamps bright enough to cross the distance. Webb sees the cosmic shore in much the same way. Its earliest confirmed galaxies may be the luminous exceptions of their age. Around and beneath them could lie a far larger population of smaller systems, each contributing modest amounts of starlight and ionizing radiation. Researchers estimate that hidden population by counting the galaxy's web can detect and modeling those below the limit. The calculation matters for reionization. Bright galaxies alone may not have produced enough ultraviolet radiation to transform all the hydrogen between galaxies. Numerous faint systems may have supplied much of the missing light. To understand the early universe, astronomy must therefore do more than find a record holder. It must measure a population. How many galaxies existed at each brightness? How rapidly were they forming stars? How much ultraviolet light escaped from them? How quickly did their numbers change with cosmic time? A record draws attention to the edge. A population explains what happened there. Webb surveys different regions of sky to build that larger view. Some fields cover wider areas and are more likely to contain rare bright objects. Others observe smaller regions much more deeply, searching for faint galaxies that represent the quieter majority. Galaxy clusters add another method. Their gravity bends and magnifies light from objects behind them. A source too faint for Webb to detect directly may become visible when a foreground cluster acts as a natural lens. The magnification is useful, but it comes with complications. The source can be stretched into an arc, split into multiple images, or brightened by an amount that depends on the cluster's mass distribution. Astronomers must model the lens before they can reconstruct the galaxy behind it. Again, the oldest light reaches us through layers. It passes through expanding space. It encounters hydrogen. It may be bent by foreground gravity. It enters a cold telescope. It becomes an electrical signal. Then, models are used to trace the journey backward. No single step restores the galaxy exactly as it was, but together, the steps recover enough of the signal to place it near the beginning of luminous history. The photons do not carry a label saying how old they are. Their age is read from stretching, absorption, atomic structure, and the measured expansion of the universe. For more than 13 billion years, those waves became longer while the space around them grew. Now, they arrive at Webb as infrared light, faint but still ordered, and within that order, the distance becomes time. The surprise is not that galaxies existed so early. Cosmologists expected gravity to begin gathering matter soon after the first atoms formed. They expected stars to ignite inside dark matter halos and small galaxies to emerge from those first concentrations. The surprise is how much light some of those galaxies produced and how quickly they appear to have organized the material available to them. In the nearby universe, a galaxy's ultraviolet brightness is often linked to the birth of massive stars. These stars burn hot and release large amounts of short wavelength light. They also live briefly, so a strong ultraviolet signal usually points to star formation happening now, or having happened only a few million years earlier. When Webb began finding many bright sources at redshifts above 10, astronomers had to ask what made them so luminous. One possibility is that the earliest galaxies converted gas into stars more efficiently than many models assumed. A young halo could draw in streams of nearly primordial gas. If that gas reached the central regions without being heated or expelled, dense clouds could form stars in rapid episodes. The galaxy might remain faint for a time, then brighten sharply as many massive stars appeared together. This uneven growth is called bursty star formation. It does not require a galaxy to sustain the same rate for hundreds of millions of years. A brief episode can make a small system visible across cosmic time. After the most massive stars explode, their energy may disturb the remaining gas. Star formation can decline, then begin again when new material arrives. Webb may therefore be selecting galaxies during their brightest moments. A galaxy between bursts may remain below the detection limit, while a similar galaxy caught during an active phase enters the survey. The early population could be much larger than the visible sample suggests. Another possibility concerns the stars themselves. The first generations formed from gas containing few heavy elements. With less carbon, oxygen, and iron, stellar interiors and atmospheres behaved differently from those of many stars around us. Low metallicity stars can be hotter and release more ultraviolet radiation for the same amount of stellar mass. A galaxy may therefore look unusually bright, without containing as many stars as an initial estimate suggests. The distribution of stellar masses also matters. In nearby regions, low-mass stars are far more common than very massive ones. But the conditions of the early universe may have favored a different balance. If young galaxies formed a greater share of massive stars, they would produce more ultraviolet light, more ionizing radiation, and more rapid chemical enrichment. They would also change quickly, because massive stars complete their lives in only a few million years. The evidence is not yet sufficient to establish one universal early stellar pattern. Some galaxies may have formed stars with a familiar range of masses. Others may have been shaped by lower metallicity, higher gas density, or stronger radiation fields. Webb is turning what was once a theoretical question into something that spectra can test. Black holes add another source of brightness. Gas falling toward a black hole can be heated to high temperatures before crossing the region from which light can no longer escape. The glowing material outside that boundary may outshine the surrounding stars, especially in a compact young galaxy. Some early sources, first interpreted as extremely massive galaxies, have become less troubling after an active black hole contribution was included. If starlight alone is assumed, a bright source may seem to contain an enormous population assembled in very little time. If part of the brightness comes from an actively feeding black hole, fewer stars may be required. The adjustment does not remove the mystery. It replaces one rapid growth problem with another. How did a black hole become large enough to shine so strongly when the universe was still young? A black hole left by the death of a massive star may begin with several or tens of solar masses. To reach millions of solar masses within a few 100 million years, it must grow through sustained feeding, repeated mergers, or periods when material falls inward at unusually high rates. Another route begins with a heavier seed. Under certain conditions, a large cloud of primordial gas might collapse more directly, producing a black hole far more massive than an ordinary stellar remnant. The conditions required are still being studied. Webb cannot usually watch such a seed form directly. It can search for later signs, compact red sources, broad moving gas, or spectra that contain both young stars and an active nucleus. Each detection adds a piece to the question of how black holes and galaxies grew together. At early times, the relationship between a central black hole and its host galaxy may not yet have settled. Some black holes appear large compared with their young hosts, suggesting that black hole growth could briefly move ahead of stellar growth. Even here, caution remains necessary. The sources are faint. Their light may combine several components. Dust can redden the spectrum. Gas moving in winds can broaden emission lines. Gravitational lensing can alter apparent brightness. Dust creates a similar challenge. Dust is made from heavy elements, so it cannot exist before stars have made those elements. Yet some young galaxies contain dust sooner than a simple timeline might suggest. Massive stars can produce dust in their outer layers and in supernova explosions. The grains may then grow further within dense interstellar clouds. Shocks can also destroy them. The amount present at any time reflects a balance between creation, growth, and destruction. A dusty galaxy may hide some of its ultraviolet starlight and release that absorbed energy at longer infrared wavelengths. A relatively dust-free galaxy may appear blue and bright in ultraviolet light. Chemical elements provide another clock. Oxygen seen in a spectrum means earlier stars have already manufactured it. Carbon, nitrogen, and neon trace other processes and timescales. Their abundance ratios can show whether enrichment came mainly from the most massive stars or whether other stellar sources had time to contribute. In some early galaxies, Webb has measured strong emission lines from highly energized gas. These lines may indicate intense star formation, low metallicity, a hard radiation field, or activity around a black hole. Researchers compare several lines at once because one feature rarely settles the question. The spectrum becomes a conversation among atoms. Hydrogen reveals where gas has been ionized. Oxygen gives evidence of stellar ancestry. Carbon and neon help describe temperature and radiation. The width of a line records motion, from rotation to turbulence or outflow. A galaxy that appears as a red speck becomes a place where gas is falling inward, stars are forming, radiation is escaping, and enriched material is moving through space. These processes also affect reionization. A galaxy can produce many ionizing photons and still contribute little to the wider universe. If those photons are trapped by gas and dust, to change intergalactic hydrogen, some portion must escape. Astronomers look for indirect clues. compact star-forming regions, strong emission lines, blue ultraviolet slopes, and Lyman alpha light that has crossed the surrounding neutral gas. The detection of Lyman alpha from a galaxy, seen about 330 million years after the Big Bang, was especially informative. At that time, neutral hydrogen should have absorbed much of this light. Its survival suggests the galaxy may have occupied an ionized bubble, perhaps created by itself and nearby sources. One galaxy alone could not clear the whole universe, but groups of galaxies could open connected regions around them. Bright objects may have marked the centers of these early bubbles, while numerous faint galaxies supplied much of the total radiation. This returns the story to the difference between what Webb finds first and what existed most commonly. The brightest galaxies are the easiest to detect. Active black holes stand out. Strong emission lines receive confirmation sooner. The quieter majority remains closer to the limit. As surveys deepen, that balance changes. Objects once represented by a statistical estimate begin to appear individually. Models can be tested against measurements of size, stellar mass, chemical composition, and number density. The first results led to claims that Webb had broken cosmology. The evidence does not support that simple conclusion. The standard model still provides the large framework in which dark matter gathers, space expands, and structure grows. The new observations are pressing most strongly on how gas entered halos, how quickly it formed stars, how strongly stars pushed back, and how early black holes began feeding. Near cosmic dawn, these processes operated under conditions that no longer exist in the same form around us. There was less heavy element cooling. The background radiation was warmer. Galaxies were denser. Gas arrived rapidly. Mergers were common. The first stellar generations were changing the chemistry as the systems themselves were still assembling. Webb has not found an impossible universe. It has found an early universe that used its available time with remarkable efficiency. A few 100 million years may seem brief beside 13.8 billion years. But within a galaxy, millions of years can contain many generations of massive stars, repeated bursts of formation, supernova enrichment, inflowing gas, and the growth of a central black hole. Cosmic time was young, physical time was already busy. From the listener's present moment, the whole period can feel compressed into one distant red point. The spectrum opens that point and separates its histories. Some light came from stars. Some may have come from heated gas around a black hole. Some was absorbed and released again by dust. Some passed through bubbles carved into neutral hydrogen. The brightness was not one thing. It was the combined result of matter learning very early how many different ways it could shine. A record in astronomy is often a temporary name for the edge of a measurement. For a time, one galaxy sits farther back than every other confirmed source. Then a deeper image is taken, a new candidate is selected, and another spectrum extends the boundary by a few million years. The change may seem small beside the age of the universe, but near cosmic dawn, a few million years can matter. Massive stars can form and die within that interval. A young galaxy can brighten during a burst of star formation. Heavy elements can be released into surrounding gas. An ionized region can expand around a cluster of early galaxies. The frontier is not only moving across distance, it is moving through a period when the cosmos itself was changing rapidly. Before Webb, the most remote confirmed galaxies were generally seen several 100 million years after the Big Bang. Hubble had approached the boundary through deep imaging, but its wavelength range limited how far the redshifted light could be followed. Webb opened a longer infrared window. Within its first years of science, galaxies were confirmed from times earlier than many previous surveys could reach. One record followed another as candidate lists were tested with spectroscopy. JWST Z14 became one of the defining objects of that new frontier. Its light left when the universe was about 300 million years old. Spectroscopic observations placed it at a redshift a little above 14. The galaxy was unexpectedly luminous, and later mid-infrared measurements indicated that oxygen was already present within it. That oxygen carried a history. It could not have come from the Big Bang in any meaningful abundance. It had to be made inside stars. Those stars then had to return it to space, where it entered the gas of a galaxy, still living near the beginning of cosmic structure. The observation compressed several stages of evolution into a narrow span of time. Gas had gathered. Stars had formed. Some had completed their lives. The galaxy had already become chemically different from the material from which the first stars were born. Then the boundary moved again. Mom Z14 was identified in a wide survey designed to search for bright galaxies at extreme redshifts. NIRCam imaging first marked it as a candidate. NIRSpec then separated its faint light and measured a sharp spectral break associated with hydrogen. The resulting redshift was about 14.44. Within the standard model of cosmic expansion, Webb was seeing the galaxy roughly 280 million years after the Big Bang. Only a modest interval separated it from JWST Z14 yet. That interval carried the record closer to the period when the first substantial populations of stars were assembling. Mom Z14 is compact. Its measured light comes from a region far smaller than the full span of the Milky Way. Much of its ultraviolet output appears to have been produced by a young stellar population, with little evidence that dust had strongly dimmed the signal. The galaxy also shows signs of rapid recent growth. Its stars were not forming at one unchanging rate. The evidence points toward an increase during the final few million years before the light escaped. Webb may have caught the system during a brief luminous phase when its newest stars made it visible across nearly the whole history of space. This is one reason record holders must be interpreted carefully. The most distant galaxy detected is not necessarily a typical galaxy from its age. It is one that happened to become bright enough in a region of sky that happened to be observed during a phase that happened to leave a measurable signal. There may have been many smaller galaxies around it. Some could have contained fewer stars. Some may have been between bursts of activity. Others may have been hidden behind foreground objects or remained too faint for present surveys. The record holder is a lighthouse, not a census. Its brightness reveals that at least one galaxy could develop rapidly by that time. It does not show that all early galaxies followed the same path. Astronomers need many fields to learn the difference. A narrow, deep observation can reach faint objects, but samples only a small part of the universe. A wider survey covers more cosmic territory and has a better chance of finding rare luminous systems, though it may not probe as deeply. Both approaches are necessary. The early universe was not uniform at the scale of individual galaxies. Matter gathered more quickly in some regions. Dense environments produced halos sooner. Other areas remained comparatively empty. This variation is called cosmic variance. A survey pointed toward one patch of sky may find several bright early galaxies. Another survey of equal quality may find fewer, not because the instruments disagree, but because the sampled regions developed differently. The solution is not to choose one field as representative. It is to combine many fields spread across the sky and gradually build a population large enough for the local differences to average out. Each observing program contributes a portion of that map. One may discover candidates, another may obtain spectra, a third may study the same galaxies at longer wavelength. Ground-based observatories can add measurements at wavelength. Webb does not cover. Numerical simulations then test whether a universe governed by the measured laws of physics can produce similar populations. The work rarely belongs to one telescope or one team. A galaxy may be selected by researchers examining images made for another purpose. Its spectrum may be collected months later. Its chemical properties may require additional observing cycles. Independent groups may reprocess the data, revise the lensing model, or propose a different explanation for the source's brightness. Knowledge grows through this overlap. It does not move as a single announcement from uncertainty to certainty. A candidate becomes stronger, a measurement becomes narrower, an interpretation survives alternatives. Even a confirmed redshift does not settle every property of the galaxy. Stellar mass depends on assumptions about the stars producing the light. Star formation rates depend on models of age, dust, and chemical composition. The possible presence of an active black hole can change the inferred balance between stellar and non-stellar emission. Mom Z14 has also drawn attention because of unusual chemical hints in its ultraviolet spectrum. Nitrogen appears strong relative to carbon. Similar patterns have been found in some other distant galaxies and in certain dense stellar systems closer to us. Several explanations are possible. Rapid enrichment by particular kinds of massive stars may have altered the gas-dense clusters, could have allowed material processed inside stars to become concentrated. A small active nucleus might contribute to some spectral features. The present evidence does not require one final answer. It provides a clue that early chemical evolution may have followed routes that are uncommon in nearby galaxies. There is another clue in the light that did not appear. Neutral hydrogen surrounding a galaxy can absorb radiation near the spectral break and create a broad damping feature. In a mostly neutral universe, this effect should be strong. The spectrum of Mom Z14 may indicate that its immediate surroundings were not completely neutral. Perhaps the galaxy and neighboring sources had already created a partially ionized region around themselves. Perhaps radiation escaped through openings in the surrounding gas. The interpretation remains under study, but it connects one small galaxy with the larger transformation of reionization. A compact source becomes evidence about the space between galaxies. Its stars do not merely illuminate their own system. They alter the medium through which later light must travel. This is how Webb approaches a period it cannot observe as one continuous scene. It measures separate galaxies. It examines the absorption between them. It compares spectra from slightly different times. From those fragments, researchers reconstruct the changing balance between neutral and ionized hydrogen. The process resembles watching the arrival of dawn from scattered windows. One window shows a brighter horizon. Another still faces dark. A third reveals light reflected from a cloud before the sun itself is visible. No single view contains the whole transition, but together they show that the night is ending. The first confirmed galaxies are such windows. Their redshifts locate them in time. Their spectra reveal the gas within and around them. Their number tells us how frequently luminous structures had already formed. Their differences show that cosmic dawn did not advance everywhere at once. As Webb continues observing, Mom Z14 may keep its record for a while, or it may give way to another source. A future galaxy might be found at a higher redshift but require years of follow-up. A candidate may appear earlier and then move closer after spectroscopy. Another may be magnified by a galaxy cluster, allowing Webb to detect a system too faint to see without the aid of foreground gravity. The sequence of names will change. The purpose beneath them will remain. Astronomers are not searching only for the winner of a contest in distance. They are trying to learn when galaxies first became common, how fast they formed stars, what kinds of stars they contained, and how their radiation changed the universe around them. The oldest confirmed light is a marker placed on an unfinished map. Beyond it lies a period Webb has not yet reached. There may be fainter galaxies whose photons already sit inside existing data, not yet recognized among the noise. There may be systems that require longer exposures. The first stellar clusters may remain beyond direct detection even after the earliest galaxies are found. The edge is shaped by nature, but also by patience. Hours of observing become deeper images become candidates, candidates become spectra, spectra become measured histories. Tonight, while the telescope holds its orientation far beyond Earth, photons from still earlier sources may already be falling across its mirror. Some will be recorded, some will remain too faint, and some may be waiting inside the data for a later generation of observers to notice where the universe first began to glow. Beyond the oldest confirmed galaxy lies a region that is not empty, but increasingly difficult to measure. There were earlier sources. There were smaller halos, younger clusters, and stars forming before enough matter had gathered to create galaxies bright enough for Webb to recognize. Their light may still be traveling toward us. The difficulty is not that nothing exists beyond the present record. The difficulty is that the signal becomes weaker while the universe around it becomes less transparent. At greater redshifts, the spectral break caused by hydrogen moves farther into the infrared. More of the galaxy's original ultraviolet light disappears from Webb's shorter wavelength filters. The remaining signal is spread across a larger distance and weakened by cosmic expansion. The galaxy also appears smaller on the sky. Its stars may be few. Its period of brightness may be brief. Even a telescope with a mirror wider than a house must gather patiently. Longer exposure can reveal fainter objects, but exposure time does not solve every problem. Background light continues to accumulate. Detector noise remains. Foreground galaxies overlap distant sources. A small red mark can be divided among only a handful of pixels, leaving little information about its shape. Eventually, the search approaches a limit where additional observation produces uncertainty faster than clarity. This is not a single, fixed boundary. The limit changes with the target, the wavelength, the surrounding field, and the observing method. A bright galaxy may be found at a greater distance than a faint one. A source behind a massive galaxy cluster may become visible through gravitational magnification. A strong emission line may confirm a galaxy whose continuum light is almost undetectable. Nature occasionally provides its own telescope. A galaxy cluster bends the space around it. Light passing nearby follows that curvature, producing distorted and magnified views of more distant objects. An early galaxy can appear as an arc, a stretched line, or several repeated images around the foreground cluster. The magnification may be enough to lift a faint source above Webb's detection threshold. But the lens does not provide a simple enlargement. The amount of brightening depends on the exact path of the light through the cluster's gravitational field. Researchers must map the cluster's galaxies, dark matter, and hot gas to estimate how the background image has been altered. Different lens models can produce different answers. A galaxy may appear 10 times brighter than it truly is, or considerably more. Its reconstructed size and luminosity depend on how accurately the foreground mass is understood. The telescope gains reach, but the interpretation becomes more delicate. There is also the possibility of detecting an individual star. At ordinary distances, even Webb cannot isolate a single star near cosmic dawn. The light is too weak, yet if a distant star passes close to the strongest magnifying region of a gravitational lens, its brightness can rise dramatically. Smaller objects within the foreground cluster, including individual stars, can add temporary microlensing effects. For a limited time, one distant star may become visible where an entire stellar population had previously blended into a faint background glow. Several highly magnified stellar candidates have already shown that such alignments can extend observation to individual stars at immense distances. A true primordial star would be a different prize. Population 3 stars are expected to contain almost no heavy elements. Their spectra would reflect gas close to the chemical state left by the Big Bang. Many models suggest they were hot, massive, and brief, though their full range of properties remains uncertain. Finding one directly would require several conditions to align. The star would need to be luminous. Its light would need to escape its surroundings. A foreground lens might need to magnify it strongly. Webb would need to observe during the period of magnification, and the spectrum would have to distinguish the star from a compact cluster or an actively feeding black hole. The absence of heavy element signatures would be suggestive, but absence is difficult to prove in a faint spectrum. Weak lines may simply fall below the noise. For now, the first stars remain easier to study through their effects. They ionized hydrogen. They changed the chemistry of gas. They produced the earliest supernovae. Some collapsed into black holes. Their radiation entered later galaxies, even if the stars themselves cannot yet be separated. A person standing beneath a dark sky can recognize constellations because human vision joins separate points into a pattern. Cosmology performs a related act across time. No single early galaxy explains cosmic dawn. No isolated spectrum contains the complete story. The pattern appears only when many partial observations are placed together. The abundance of bright galaxies constrains how quickly dark matter halos grew. The ultraviolet slopes of their spectra help describe their stars and dust. Emission lines reveal energized gas and chemical enrichment. Absorption by neutral hydrogen shows how reionization progressed. The cosmic microwave background supplies information from a much earlier time. Later galaxies reveal what the early systems eventually became. Between these records, simulations connect stages that cannot all be observed directly. A simulation begins with the small density variations measured in the early universe. Gravity draws dark matter into filaments and halos. Gas follows. Cooling and compression lead to star formation. Stars release radiation, winds, and heavy elements. The calculation then produces a model universe that can be viewed as a telescope might see it. Researchers compare its galaxies with Webb's galaxies. Are there enough bright systems? Are their sizes similar? Do they form stars at comparable rates? Does reionization happen at the correct time? When the answers disagree, some part of the model may need adjustment. The problem could lie in star formation efficiency, stellar feedback, dust, black hole growth, or the resolution of the calculation. It could also reflect the small number of known galaxies and the uneven regions sampled by current surveys. Models and observations move toward one another. The data become broader, the simulations become more detailed. Neither side remains fixed. Future telescopes will continue this work from different directions. The Nancy Grace Roman Space Telescope is designed to survey wide regions of the infrared sky. It will not replace Webb's deep spectroscopy, but its broad view can identify rare objects and map the environments in which they appear. Extremely large ground-based telescopes will gather spectra with mirrors far wider than those currently in operation. Earth's atmosphere blocks some wavelengths and adds distortion, but adaptive optics and large collecting areas will allow detailed study of selected distant galaxies. Radio observatories seek another kind of record. Neutral hydrogen can emit radiation at a wavelength of 21 centimeters. Expansion stretches this signal to much longer radio wavelengths by the time it reaches Earth from cosmic dawn. Mapping that radiation could reveal where neutral hydrogen remained and where ionized bubbles had formed around the first stars and galaxies. Instead of observing only the luminous sources, radio astronomy may eventually show the medium surrounding them. One approach sees the lamps, the other traces the darkness between them. Together, they could create a three-dimensional history of reionization. Farther in the future, proposed space observatories may use larger mirrors in different wavelength ranges to detect fainter galaxies, study early black holes, and measure chemical elements with greater precision. No design removes the horizon completely. A larger telescope reaches farther, then encounters another limit. A more sensitive detector reveals weaker sources, then meets a new background. Better resolution separates structures that were once blended, while still earlier systems remain unresolved. Observation advances by moving the boundary, not by abolishing it. There will always be light too faint to gather. There will be events whose photons never reach us. There will be regions beyond the observable universe, separated from us by the history of cosmic expansion. This does not make the accessible universe incomplete in a disappointing way. It gives every measurement a location. Webb occupies one point in cosmic history, receiving the light that can reach that point now. Its oldest galaxies are not chosen by human preference. They are selected by distance, expansion, brightness, and the age of the telescope's own observing moment. A civilization billions of years from now would see a different cosmic boundary. Some galaxies visible to us will have faded beyond its observable reach. Other records will remain in local stars and relic radiation. The night sky itself will have changed. Our view is temporary. But temporary does not mean insignificant. For a brief interval in the history of the universe, mirrors built near one ordinary star can collect light from the first few 100 million years. The atoms in those mirrors were made by later generations of stars. The minds interpreting the spectra appeared after billions of years of chemical and biological change. The early universe could not observe itself. Much later, part of its matter became capable of looking back. The result is not a complete image of the beginning. It is a sequence of faint signals, each carrying a little more structure than the last: a hydrogen break, an oxygen line, a compact shape, a redshift measured through patient exposure. Beyond the current record, earlier light continues to cross the expanding universe. Some of it may one day enter an instrument that has not yet been designed. Some may already rest inside observations, waiting to be understood, and some will remain beyond the reach of every mirror we can build. The oldest light Webb can find is not a fixed object waiting at one permanent address. It is a moving boundary between what has already been measured and what still lies below the sensitivity of the instruments. Every confirmed galaxy near that boundary makes the darkness behind it more specific. The unknown becomes narrower. The questions become better formed. At first, the search may seem to be about distance alone. Which source is farthest? Which redshift is highest? Which name belongs at the top of the list? But the deeper purpose is not to collect records. It is to understand a transition. There is also a limit built into the kind of light being sought. Before stars existed, there was no starlight to collect. Webb cannot extend its gaze backwards simply by exposing longer, until a galaxy appears in every earlier age. At some point, the objects capable of producing infrared light had not yet formed. Farther back lies the cosmic microwave background, released long before the first stars, and observed with instruments designed for much longer wavelengths. Between that relic glow and the earliest galaxies is an interval whose details must be assembled indirectly. The ages of the first stars, the timing of the first black hole seeds, and the growth of the earliest ionized bubbles are inferred by connecting different records. Webb contributes the infrared light of galaxies. Radio experiments seek neutral hydrogen. Microwave measurements preserve conditions from an earlier cosmos. Simulations test whether one physical history can pass through all of them. The oldest light Webb can find is therefore one layer in a larger archive. It is not the first light of any kind. It is the oldest accessible light from objects beginning to build the luminous universe we recognize. There was a universe with no stars, then stars appeared. Small gatherings of matter began to hold their shape. Galaxies formed, merged, brightened, and altered the hydrogen around them. The first heavy elements entered space. Black holes began to grow. Radiation spread through regions that had remained neutral since atoms first formed. Webb looks into that sequence from the far side of 13 billion years. It does not see every step. It receives isolated pieces separated by distance, brightness, and chance. One galaxy provides a redshift. Another reveals oxygen. Another shows a strong hydrogen line. A cluster lens magnifies a source that would otherwise remain hidden. A spectrum suggests that starlight alone may not explain all the energy present. No single object carries the complete answer. The answer forms across a population. This is why the work continues after a record is announced. A distant galaxy must be compared with others from nearly the same era. Its brightness must be placed within a wider survey. Its spectrum must be tested against models containing stars, gas, dust, and black holes. Its surroundings must be considered as part of reionization, rather than as empty space between sources. Over time, the map gains depth. A few bright objects become dozens. Dozens become a distribution of sizes and luminosities. The distribution becomes a history of how often galaxies formed, how rapidly they grew, and how much radiation they released. There may never be a moment when astronomers can point to one image and say that the beginning of galaxy formation has been fully seen. Beginnings in nature are often spread across conditions rather than marked by a single instant. The first star did not illuminate the whole universe. The first galaxy did not establish one final form. Cosmic dawn arrived in many places, at different rates, inside halos that differed in mass, environment, and history. Webb is reconstructing that uneven arrival. Its observations will also outlast the first interpretations made from them. Data gathered for one program can be examined again years later with improved calibration, different software, and new questions. A faint feature dismissed as noise may become meaningful when another telescope observes the same region. A galaxy classified one way may reveal a hidden component after longer wavelength measurements are added. The photons do not change after reaching the detector. The understanding of them can. This is one of the quieter strengths of astronomy. The universe provides no explanation beside the signal. It sends light, gravitational influence, particles, and motion. The explanations are built slowly, with measurements that agree or fail to agree. A red point becomes a candidate becomes a spectrum becomes a redshift becomes a location in cosmic history. Then that location becomes part of a larger account that may be revised as the evidence grows. Nothing in this process makes the early universe less remote. The light remains faint. The galaxies remain beyond any journey available to us. Their present forms are unreachable by observation because the information has not had time to arrive. Yet distance does not prevent contact altogether. The contact is one-way and delayed, but it is real. Atoms in a young galaxy released photons. Those photons crossed expanding space. Some passed through hydrogen, some near intervening galaxies, some through regions shaped by gravity. A small fraction entered Webb's mirror. From there, they became charge within a detector, numbers in a file, patterns on a screen, and eventually part of a human description of the universe. The chain is long, but there is no break in it. The same light that left an early star-forming region is the light that reaches the instrument. It has been stretched and weakened, but not replaced by a representation. The representation comes afterward. This gives the oldest light a peculiar nearness. Its source is almost unimaginably far away in time, yet the signal arrives here. It touches a mirror built from matter made in later stars. It enters detectors designed by a species that appeared near the end of the journey. The early universe and the present do not meet in a physical place. They meet in observation. Webb will continue turning toward selected fields, settling into position and collecting infrared light. Some observations will confirm ideas already forming. Others will complicate them. New record holders will appear. Some candidates will fade under closer study. The first galaxies will become less like isolated curiosities and more like members of an emerging population. The unknown will not disappear, it will move. Beyond the earliest confirmed galaxy, there will still be fainter systems. Beyond the first populations Webb can infer, there may remain individual stars that no current instrument can separate. Beyond every observation lies the larger fact that the observable universe is only the portion from which light has had time to reach us. Still, the boundary is no longer where it was before Webb opened its mirror. A period once described mainly through equations and simulations now contains measured galaxies. Their spectra show gas in motion, heavy elements already present, and radiation leaving systems only a few 100 million years after the beginning. The edge of time has acquired detail. Not complete detail, not final answers, but structure. As this episode closes, the telescope remains far beyond Earth, keeping its sunshield toward the warmth and its mirror toward the sky. The oldest light continues arriving without ceremony, mixed with the light of nearer stars and later galaxies. The instruments receive what they can, the rest keeps traveling, and somewhere inside that long infrared night, the first galaxies are still becoming visible.